Well, this is Mr. Price. I'm launching on a new adventure that I've never tried before, but that's what life is like, and certainly adversity is what di differentiates Christians. How do we respond to things that are different and sometimes even adverse circumstances? So to my physics class, who I hope eventually will benefit from this effort, I am hopefully going to show you how to solve some of the problems that I assigned on the problem set. So if you have that with you, you can follow along. But I'm going to pray for my own sake, and maybe it'll help you all too. Dear God, help me to show your glory, the wonders of the order of the universe that you have created for us, that we would understand sound better through this and through the math and the equations and being able to predict, calculate results from things that we know in our surroundings, that we can taste and see that you are good, but we can listen and see that you are good. We can calculate and see that you are good. In Jesus' name, we do these things. Amen. So the first question, we'll get us through as many of these as possible. What is the wavelength of 55 hertz? And that is in parentheses as A. That just means the note on a piano. 55 would be an A, very low A. Double that, it'd be 110. That would be an A. Double that again, it'd be 220. That would be an A. And double that again, and it would be 440, which is an A. That is what we usually use as a standard for tuning in music. And that would be the A above middle C, if you're kind of picturing that on a piano. So 55, a very low A, from a tuba in 20 degrees centigrade air. Well, we would have to know what is the velocity of sound. This is question number one. So the velocity, of course, is going to be the wavelength times the frequency that we were given. So we're asked for the wavelength, so we would want to rearrange that. Wavelength would be the velocity divided by the frequency. But we have to do a little side thing here where, what is the velocity at 20 degrees? The velocity at 20, the velocity of sound in air, that is. And I realize this is board that keeps bouncing around. The velocity of sound in air at 20 degrees. What did we give that? We'll have to pause and look that up. I think we're recording again. Anyway, 346 is at 25 degrees Celsius. So we have to adjust that a little bit. It's going to slow down a little bit at 20 degrees. How much does it slow down? Well, it slows down 0.6 meters per second for every degree, and times 5 degrees, because it's 5 degrees different than 25. So we subtract off 3 meters per second. So what does that give us? That gives us 343 meters per second as the speed of sound. There. Now we can go back to this equation. So the velocity of sound is 343, not 346, 343 at 20 degrees meters per second. Divide that by the frequency of 55 hertz. If you like to see the unit labels eliminated, that would be 55 per seconds. Of course, that means that if you divide meters per second by per seconds, or hertz, that's I'm going to give you the label meters, which would be, what do you get? All right, who does the calculations? Jackie? Caleb? Carson? Who's got that? 343 divided by 55. 6.2? Is that what you got? 6.2 meters. It is a low frequency. That's a pretty long wave. Okay, there's question number 1. Let's pause. Let me erase that. All right, let's go on. I got question number 1. Number 2, what happens to the velocity of sound as the air in a horn warms up? Anybody in band knows that you got to warm up the air in the horn before you tune, because speed of sound is faster in warm air. So what happens to the velocity of the sound? It goes faster in warm air. What happens to the wavelength of the sound as the air in the horn warms up? Well, the wavelength of the sound in the air, the horn length is what determines the wavelength. So the length of the horn hasn't changed, or at least not significantly. So it would be the same. So then if the velocity goes up and the wavelength stays the same, what would happen to the frequency, which is, of course, what you would hear? We would perceive that as pitch. So this is question number 2. Increase, right? Velocity increases. The wavelength stays the same because the length of the horn stays the same. And what would that do to the frequency? Well, from the equation that we had earlier, velocity is wavelength times frequency. If you rearrange that, frequency, what's going to happen if the velocity divided by the wavelength? Well, if the velocity goes up, wavelength stays the same, the velocity should also increase, right? Which means the pitch goes up. So if you tuned before you warmed up your horn and then got warm air in your horn, it would go sharp. The pitch would go up just a little bit. How about number 3? Disregarding the diameter correction for the closed tube. How long is the fundamental for a closed tube that is 1 meter long? Okay. There's a little bit of correction for big tubes and small tubes, the diameter of the tube. But if you look at number 3, let's just draw a tube like that. The fundamental, the first harmonic for a closed tube, now that would be closed on one end. Oh dear. Let's make that tube shorter because it'll make it easier for me to draw. If it's closed on one end, opened on the other end, that means there's going to be phase inversion there because you've got free room air, a free tube air, I should say, that strikes that back wall, and equal forces are exerted, but which one's going to move more easily, the air or the back wall? Obviously, the air will move more easily. So I know we have to draw these as crests and troughs. They're actually compressions and rarefactions, but I'll draw it graphically. The pressure would be high there. You might call it a crest if you want to. It hits the back wall and flips over and becomes a trough. So if we represent the wave as a transverse wave, even though it's actually a compressional or a longitudinal wave, that's a way of representing that. Well, from, as you know, on strings that we vibrated in the class, at the front of the class, the part of a wave from a node to an antinode is only 1/4 of a wave. So that represents, I should say, the tube length represents 1/4 of a wave length. So the question is, then how long is the fundamental if that's 1 meter long. Well, if 1 meter is 1/4 of a wave, then the length of the tube would be, or the wavelength rather, would be 4 meters long, because the length of the tube is actually 1 meter long. That would be a pretty long wave. The wavelength of the 55 hertz that we calculated in number 1 was 6 meters long. That would be a pretty long wave. So this would be a pretty low note if we were actually producing a note. Let me pause and I think we're recording again. We'll try number 4. If you need to, you can stop anytime, of course, and take a nap, talk to each other on your phones and things like that. That's one advantage, I guess, that you have of doing this online. So number 4, we've got a mine explodes at sea. There's an interval of 5 seconds between the sound heard in water and the sound heard in air. In which will the, let's say, you're on a ship. You've got classic water waves there. Let's see, the ship's going to be partly underwater, right? The waves, maybe. Yeah, you're already laughing at my drawings. Okay, I guess you would see them on the side of the ship. You wouldn't see the bottom of the ship, though, would you? Not very well. We got, of course, this is the naval ship Comfort, the hospital ship that's on its way to help the coronavirus patients. Actually, the way I heard it was that they were going to take the regular hospital patients and put them on the ship for the typical things that they're going to do, and they're going to use the land hospitals then for the coronavirus patients in New York. So yeah, be in prayer for those folks. There are people dying from this virus. I guess it's not just a cold. So we've got the ship there, but we have a mine that explodes at sea. Boom. It's underneath the water, right? Explosion. Boom. And the sound from that, which is of course compressional waves, will it travel faster in the water or faster through the air? So we've got compressions and rarefactions, the squish and the spread. Well, it travels faster in water. So we're going to have to know what the speed of sound in water is. Let's pause and look that up. I found 1,531 meters per second in seawater. That would be the speed of sound. In air, of course, it's going to be at 20 degrees. That's a nice cool temperature, 343 meters per second. So it's going to arrive sooner. What is the same for both of these? Whether the sound travels through the air, it'll be slower. Traveling through the air, spread, squish, or whether it travels through the water, the thing that is the same for both trips is the distance, right? The distance could be expressed one of two ways. It could be this as the velocity of sound in air times, air times time. Or it could be expressed as the velocity of sound in water times time. But those two times aren't the same, are they? It says in the problem that it takes 5 more seconds to get there in the air. So whatever the time is for the trip in the water, the trip in the air is going to be t plus 5. Oh my gosh, we've got some algebra. Oh, that means this distance and this distance are the same, so the velocity of sound in water, let's go ahead and put in a number, I'm running out of room. Velocity of sound in water, 1531 meters per second, times how much time? Well, it was t, right? That's all we know. We don't know how much time it was. We just know it took 5 more seconds in the air. Well, that should be equal to the velocity of the sound in air, 343, times t plus 5 seconds. There you go. Solve that equation for t. And then, of course, you can plug that back into one of these equations for distance, and you'll know how far away the sound was. I'll give you a chance to do that. I'm going to pause. Okay, you see what we've got. 1531 t equals 343 t plus 343 times 5. We just distributed 343 times t plus 5. And then we get 1531t minus 343t equals 343 times 5. 1188t equals 1715. I left the unit labels off, but here the unit labels are on there. T then equals 1715 meters divided by 1188 meters per second, which I guess we punch that in. 1715 divided by 1188. What do we got? 1.4 seconds. To go back now and find out how far that is, let me pause and erase. Okay, we got more room. With t being 1.4 seconds, you can go back to either one of the distance equations. I just picked the one with the seawater. Sound travels 1531 times 1.4 seconds, because that's the equation. It was just t in the seawater. If you use sound in air, it would be 343 times t plus 5, so that'd be times 6.4. And either way, you should get the same distance. 2,000, to two significant figures, 2,100 meters per second. Oops, distance. That would be meters. Thank you for correcting me, whoever it was that said wrong label. Tori, is that what you? Yeah, okay. I realize how boring this is when I'm doing it at home in my living room. Anyway, hey, but then again, it was kind of fun to see the order of God's universe. Let's pause that and get ready for number 5. All right, we're back. Number 5. The vibrating part of the G string on a violin has a linear density of 3 times 10 to the negative third kilogram per meter. It is 330 millimeters long, or 0.33 meters long, has a tension of 50 newtons. What is the fundamental vibrating frequency? So we can use, again, these ideas and predict what frequency that string is going to vibrate at before we ever build it, and maybe it's on a guitar or a piano or a violin or whatever it is. In this case, it's a violin. This equation, relationship between velocity, frequency, and wavelength, this equation simply represents that the fundamental, sometimes we write the little f here, fundamental, or spell it fund, that wavelength would be twice as long as the string is. If you remember the appearance of that string vibrating, it made a big antinode right there in the middle, like that. Well, that's only half of a wavelength. the actual wavelength would be twice that long. So again, and then the last equation here, I didn't finish it. I was looking it up. Mersenn's equation, they use the symbol F for tension. F, of course, is force. And then they use the symbol mu for the density of the string, the density per unit length, or sometimes it's called the linear density. So these three equations together, we can talk about the fundamental frequency. Another way of symbol for that is fundamental O for original or fundamental. It's 1 over 2L, as you can see that, and the velocity then would be the square root of the tension divided by the linear density, mu. So there, it's a little more complicated, but these are still very orderly predictions using the marvel of God's orderly universe and equations, math, the language of God. All right, if you can kind of see how I got from those three equations to this one, then we can use it now. We just plug in and predict. So we've got linear density is given 3 times 10 to the minus third kilogram per meter. That would be this number. The tension is 50 newtons, and the length of the string 330 millimeters. So here we go. 1 over 2 times 0.33 meters times the square root of 50 newtons of tension divided by the linear density of 3 times 10 to the negative third kilogram per meter. And we ought to double check with all these complicated unit labels, make sure that we're in the fundamental units. If we stick with the fundamental units, then we should be all right without having to write out what the Newton is actually a kilogram meter per second squared. So as long as we're in kilograms, meters, newtons, we should have our frequency then should be in per seconds or hertz. So wow, let's pause that and punch that in. Okay, this is what it looks like. 1 over 2 times 0.33. I got 1.515 repeating and 50 newtons divided by 3 times 10 to the minus third kilogram per meter and square rooted 129.1. You might practice that with your calculator and instead of just writing it down and see if you get 196. I suppose, can we keep 3 significant figures? Technically, we've only got 2. So we'd probably have to round that to 200, then hertz, and that's second, the first 0 there would be a significant. Yeah, if you check your note chart, that would be the G below middle C. All right, let's clean our board. Move on. Isn't this fun? Yeah, number 6, we're looking at the inverse square law, which is kind of the way a lot of phenomena spreads out. Forces like gravitational force, we know from our earlier studies that if you get twice as far away from the Earth, you only feel 1/4 as much force because the intensity spreads out in 2 dimensions as it travels in a 3rd dimension. I was trying to diagram it here. My drawings aren't really good, but there's supposed to be a 3-dimensional aspect to this, so that if a square containing this much sound was 1 meter on a side, that would be the depth and the height. As it moves 1 meter away, that would be sound contained in a 1 square meter area. But what if you doubled your distance? Well, that same square that had to contain that same amount of sound, it would have to be twice as big in 2 dimensions, which of course would make it 1/4 the size, whereas the area of this first rectangle would be 1 square meter. The area of this square would be 4 square meters. So we've spread it out over 4 times as much area, which means 1/4 as much sound. So if things are too loud at church, just double your distance. You get 1/4 the sound. Except that only really works outside because the sound would spread out uniformly in both dimensions. In a church, the walls are probably reflective, so it wouldn't quite work there. But at least in an outdoor concert, it should spread out by the inverse of the square of the distance. So you notice that we've said, well, if I2 over I1 then should equal distance 1 squared over distance 2 squared. So they're inverted and squared. We solve the equation for the new intensity, the I2. Well, you take the I1, that's supposed to be a 1, and then multiply times the distance ratio, inverted and squared. Inverse square law. So we can do that pretty quick. Then what do you hear at 5 meters if it's 2 times 10 to the minus 6 watts per square meter at 2 meters? So solve for I2 if the first intensity is 2 times 10 to the minus 6. Little tiny amounts of energy we can hear. Watts. That's 2 millionths of a watt spread out over a square meter. Not only can we hear that, but it's actually pretty loud. Our ears are very sensitive. Another marvel of God. So then our ratio is, our first distance is 2. That would be 2 meters squared divided by our new distance, 5 meters squared. So there we go. Give me a second to punch that in. There we go. I punched it in. And of course you hit 2 exponent, enter exponent on the calculator if you know how to do that. 2 EE, enter exponent, -6, and of course that gives you that very small number, and then you multiply times 2 squared is 4, divide by 5 squared is 25, and you get 3.2 times 10 to the -7th. A lot quieter just by doubling your distance. Well, in this case, the change is 2/5 as far away. Okay, let's pause that. All right, number 7. How many times louder than the threshold of hearing, which is given as, just arbitrarily, we've decided is 10 to the minus 12th watts per square meter. That's a tiny amount of energy. 10 to the minus 12th watts. So the sound of physics class is about 3.2 times 10 to the minus 7th watts per square meter. That should be a capital W. Of course, physics class right now probably runs about 40 decibel, which means 10 to the 4th times as loud as the threshold of hearing. So even with nobody there, all the noises from various things, heating and air conditioning system, particularly, produces some sound. I don't know what symbol to use for the sound intensity. It's usually a script B, but you could just write decibels, dB. But we take, first of all, we compare it to the threshold of hearing, or whatever our other sound that we're making a comparison is. If they're not otherwise stated, the sound intensity is being compared to the threshold of hearing. And we take the log of that, which just means what power do you take 10 to get that ratio, the log. It's an exponent of 10. And then we multiply 10 times that because it makes it a larger number and spreads out the scale a little bit. All right, let's try it. Well, 10 times the log of a ratio. The ratio being 3.2 times 10 to the minus 7th. Watts per square meter. Compare that to the threshold of hearing, which is 1 times 10 to the minus 12th watts per square meter. Now, gosh, if that was a 1, that'd be easy enough. You could do that in your head. Because then all you'd have to look at is dividing two numbers. We know you subtract the exponents. How much louder is 10 to the minus 7th than 10 to the minus 12th? Well, it's 10 to the 5th, right? The exponent, 10 to the 5th, is 5. We multiply times 10, we get 50. So roughly we're saying 50 decibels. But this is larger than 1. That's 3.2. So what we're really wanting to know is what is the log of 3.2. Also, we need to add that to the log of 10 to the minus 7th. Yeah, when you multiply two numbers, you add their logs. Yeah, remember Noah had trouble with two snakes that wouldn't multiply. Fortunately, they were adders, remember? Fortunately, he was a good mathematician, so he put the adders on a log table, and they multiplied. Yay! I had to throw in one bad pun. All right, that's a good math joke. So we know it's going to be more than 50 decibels. We know it's going to be more than 10 to the 5th louder. It's a 3.2. Well, if you knew what number do you take 10 to get 3.2? What exponent would 10 to the some power be? It would equal 3.2. Well, if you knew all those. But I'd say, let's use a calculator. Let me go find mine. Here we are. I know you probably can't see this display, but we would put in 3.2, enter exponent, -7. -7 equals that tiny number, and then we would divide that by 1, enter exponent, -12, -12, and then what does that equal? Yeah, very, very small number. Take the log of that ratio, log negative 6.49. And then take that times 10. Okay, that's what I should have got. and then equals, see, log, where is it? There, 5.5. And then, of course, times 10. That would be 5.5 bells, they actually call it, named after Alexander Graham Bell. But the decibel, deci meaning tenth of a bell, would be 55. 55, we said it'd be greater than 50 decibels. We estimated the difference in the log was going to be about 5. So 55. I'll write that down. I didn't get that. 55, and the unit label is decibel. Not actually a unit, because you notice that our units there were the watts of power per square meter cancels, right? So we really don't get any unit label. Decibel is actually just an expression of a ratio. It's actually the log of a ratio, which is a unitless number. Hey, more of this fun stuff with logs. If you're talking about, it's kind of interesting that our hearing actually is in powers of 10. That's essentially what we're saying. It's logarithmic. Even when you buy volume controls, a volume control is not linear. When you turn the little knob, it's actually amplifying or allowing more voltage through by powers of 10. It's actually a logarithmic progression. We hear, our ears are just amazing. They don't just hear twice as loud, they hear powers of 10 as loud. Number 8 says trombones playing at 95 decibels. Bones rule. I was a trombone player. 95 decibel, well, I know that would be 1 times 10 to the, it would actually be 1 times 10 to the 9.5 power. You see what I did there? 95 decibels, I divided by 10, I got 9.5, and I made that the exponent on the 10, so that's actually how many watts per square meter of sound intensity I get. I know that's not a real proper way to write exponents, but your calculator actually understands that. If another trombone starts playing at the same intensity level, what's the combined intensity level? Well, if you had 2 of those playing, it would be 2 times 10 to the 9.5 power. How many decibels is that? Compared to 10 to the minus 12, well, what is the log of 2? It turns out we could take that. Log of 2, put that in your calculator. 2 to the log. 2 log of 0.3. So in other words, we could say that another way to write the number 2 is 10 to the 0.3 power. Or another way of saying it, twice as loud. This is one that you could just remember. Twice as loud is 3 decibel. There. Just remember that. On volume controls, these faders that you see on a soundboard or even on your radio, sometimes that they will tell you 0 decibel will be no change. It's another way of saying 0 dB is just a way of saying it's the same coming in and going out. The voltage that goes in equals the voltage that goes out, so there's no change, 0 dB. 3 dB means you've doubled it. 6 dB would be doubling it again 4 times. So they usually talk about volume changes in 3 decibel units, increments, I should say. It's technically not a, well, what do you do when you take the log of 2 numbers? Here, let me get some more room. If that's true, then the log of 2 times 10 to the 5th would be the log of 2 plus the log of 10 to the 9.5, which of course we know what this is, 0.3, and that's 9.5. There's just the exponent. Put them together, it's 9.8. But remember, decibels is 10 times the log. So if we took 10 times all of that, right? 10 times this, 10 times this, that's 98 decibels. It's interesting that one trombone is 95 dB. 2 trombones, just add 3 dB. That's how easy it'll be on the test. We'll just have twice as much of something. Twice as much of something only raises the sound intensity by 3 decibel. If you're one of these audiophiles that likes to put gobs of stuff in your car and make it really loud, as to maybe the size of your engine isn't big enough, so you want to compensate for it with the size of your stereo. Well, think about it. If you're producing 95 decibels with the present sound system and you want to gain 3 more decibel, you'd have to double everything. You'd have to get twice as much sound just to get 98 decibels. And then twice as much again just to get 3 more decibel. After a while, it kind of reaches diminishing returns. You spend twice as much money, and you don't really get that much louder a sound. But this works with choirs and bands and everything else too. When we double, we gain 3 decibels, which is not actually. You might wonder how much louder is 3 decibel. It doesn't sound that much louder. Well, it's twice as loud, but it's because of the way our ears hear things. Our brain actually does the hearing. We hear logarithmically, and we perceive very little change. It's actually 3 decibels is a perceptible change, but it doesn't we don't think when we hear twice as loud, we don't usually think twice as loud. But it actually is 3 more decibels. Well, let's go to number 9. All right, number 9. How many times more intense is a 90 decibel sound? 90 decibels. An example of 90 decibels. Oh, I don't know if the hall at class change would be this loud. It certainly isn't now. But a basketball game, while the game is going on, maybe 90 decibel. The band performing, church worship. We try to run 85 to 90 decibel around that if the band's playing, cranking pretty good. So that's a pretty loud sound. How much louder is 90 decibel than a 40 decibel sound? Well, 40 decibel sound, I know that's awfully easy mathematics there. It's 50 decibels, right? But remember, logs add and subtract when you're actually multiplying sounds. Then you have to think differently. The 50 decibel, then, if you divide by 10, that would be 5 bells, or 10 to the 5th times. Yeah, 50 decibels is 5 bells, but that means 10 to the 5th times as loud. So you can add and subtract decibels, but they actually represent multiplying if you consider their exponents. Let's do that in number 10. A microphone itself doesn't generate very much electricity. We're going to talk about that next unit. We talk about electromagnetism. Their typical microphone has a little coil of wire, and it moves just slightly when you speak into it because of the compressional wave. It moves the diaphragm up and down. The coil of wire then moves across a magnetic field. And a wire and a magnet makes electricity. So it's actually a little generator, but it doesn't generate very much power. Our voices aren't that capable of large power outputs. Some more than others, but a microphone has an output of 10 to the minus 9th watts. So we've got, here I'll take a chance and try to draw. So we've got 10 to the, what is 10 to the minus 9th watts. It goes through a preamplifier that changes it 20 decibel. This is the way they actually mark electronic equipment. My old phonograph turntable has to have a 20 decibel preamp before it goes into the amplifier just to make it run. Well, the amplifier then has a 90 decibel gain. So really what we're asking, and you can hopefully see from this, why it's easier to talk about it in terms of decibels than it is actual power. Because I know what happens to 20 decibels if you change that to an actual multiplying factor. How much louder is that? 10 to what power? 10 to, not watt. What is power? 10 to the power of 2. Yeah, we just add, in other words, it makes it 100 times. That's another decibel that you might remember is 10 to the 2 power, 100 times is 20 decibels. So if it's 100 times louder, it's 20 decibels, which is not really a whole lot louder, but it's actually 100 times. What does 10 to what power would be 90 decibels? 10 to the power of 9, of course. There you go. So this is gaining 10 to the 9th power. What's going to come out of this finally? Well, it started at 10 to the minus 9th. You gain 10 to the 2. You gain 10 to the 9th if you want to just add the exponents. So the exponent we add here, we start with -9. We add 2. And then we add 9. And what do we get? 2. Right? Which is, if we look at it in actual power, it's 10 to the 2 power. In this case, what is the unit of power? Yes, it is. Okay, let's pause. All right, last problem. This is an effect that we're familiar with. We hear it all the time. When an object is producing a sound and it's moving, the pitch that you hear has been altered. If you look at some videos on this, they actually have good depictions of what the sound is doing. But if a moving source, of course, is producing sound waves out in front of it, then if it's moving, the distance between those will be shortened. It's a wavelength change. But you can also experience the Doppler effect with the front of this would look more like this. It's crunched up. Terrible diagrams. Watch some videos. There are really some interesting videos on Doppler effect. But if the source was stationary and the listener was moving, those would not get closer together, but the listener would be moving across those sound fronts, and he would hear them more often. More often is another way of saying higher frequency. So if the source is moving, you get a wavelength change. If the listener is moving, you get a frequency change. But even if it's just a wavelength change, ultimately what you hear is a frequency change. But it's a frequency change because of a wavelength change. Here, it's actually a frequency change because of a period change, the length of time between of those compressions that hit your ear has been shortened. So let's do the math. That's a little more definite, right? On this one, a fire engine's siren's 500 hertz. So what frequency would be heard by a stationary observer? You could actually do this the other way around, where you measure the sound heard and you know the frequency of the source. If you know those two numbers, and you know how fast sound moves, you could figure out the speed of the listener or the source. They do this, of course, with electromagnetic waves. They call them radar waves. Meteorologists use it. State Patrolman uses it also because they know these factors. It's already programmed into their speed gun. But knowing these different measurements, we can calculate one that we don't know, and it's usually the velocity of the object moving, which typically becomes the source. They bounce a radar wave off of the object. It becomes the source of the radar wave, and that's usually moving. Now, the State Patrolman could also be moving. He would be the listener. Both of those velocities would be important then in determining this effect. So, but for our problem, we actually just want to know what would the frequency change be. What frequency is heard? That would be the F heard. If there's 500 hertz being produced by a fire engine siren, I should say. What if it's moving toward him at 12 meters per second? Well, we have to know the speed of sound. What do you want to use? 25 degrees, that's a pretty balmy day. That's average. It would be 346. So the speed of sound would be 346. By the way, all this is given to you on a test. The tricky part is deciding which one of these numbers is in the problem. Well, 346 would be the speed of sound. Velocity of the listener. Well, the observer is stationary. It says, so the observer, which is the listener, is stationary. Oh, that's 0 then. I'll go ahead and write it even though it's kind of obvious. Just so you know, that number is 0. The velocity of sound, once again, is 346. Now we've got to decide, do we add or subtract the velocity of the source, which of course is 12 meters per second. Let me put 12 meters per second there. Let's use our math without a sense of logic and prediction beyond math or before the math. I don't know which way you'd think of it. But we could predict what should happen to the frequency of that sound because we have observed this in nature. If a siren from a fire engine is coming towards you, or any sound for that matter is coming toward you, would you hear a higher frequency or a lower frequency? If they're moving toward you, remember we said the diagram shows the waves are scrunched together, which would mean you would hear them more often, which means it would be a higher frequency. So now let's go back to the equation. That number needs to get bigger. If we put plus or minus here on the 12 and we solve the problem and we come up with an answer that's too small, smaller than that, we did it wrong. We need an answer that's bigger than 500 because it's moving toward us. Well, let's decide, if we subtract 12, that would make the denominator smaller than the numerator. And we know enough math. A numerator that's bigger than a denominator is a number bigger than 1. And a number bigger than 1 would make this a larger frequency. So that sounds good. Let's subtract 12. We should get 500 something. Let's put that in our calculator and see what we get. Well, I got 518. Jackie? Caleb? Carson? Whoever usually punches those numbers in. I think some of you in the back row actually punch in the numbers too, and you just don't want to say anything. James, what'd you get? Alex? Oh, he's in the bathroom. All right. 518. Can we report that many? I suppose we really only can report two significant figures, we'll say 520. 520 hertz. What if it was moving away from him? How that would change things, wouldn't it? That's all right. If it's moving away from him, it's going to be a lower frequency, sorry. Now the way to make it a lower frequency answer, what if we added 12? That would make the denominator bigger than the numerator, and that would make the number that we're multiplying times less than 1, and that would make this a lower frequency. So let's see what we get this time. What'd you get? 483 to two significant figures, I suppose we should say 480. 480 hertz. Hey, watch some of these Doppler videos. There's a whole bunch of stuff on YouTube to demonstrate these things. You can actually figure out how fast a car is going by the sound that it makes also. If you know the frequency it's producing, if it's not moving and you know the frequency, then it's pretty like say it had a sine wave generator on board that was producing a known frequency, then you could zoom past, measure the frequency, which you can get apps, by the way, that measures frequency and produces exact frequencies if you want to play around with that idea on your phone. Yeah, have somebody run past with a known frequency generator. You could measure their frequency as they run past you, do the calculation, you could figure out how fast they were going. Kind of interesting stuff. But it can be applied to a whole lot more things than just sound. Hey, great. Thanks for listening. And this completes the assignment for Chapter 12. I know this will probably take you a few days. This is actually Saturday. I'm recording this, but I will put it on the website hopefully before Monday. And the lesson plans for Monday and Tuesday at least will be for you to try to get these problems written down, because I know you can probably only stand about 10 minutes of this at a time. Anyway, miss you guys. We'll see you later.